we will solve one more problem. Yeah? This is a very simple problem, but we are going to use slightly different units. So let me read the problem first. So water containing 6.8 milligram per liter of a steroid, and we need to extract this steroid using one solvent. So we are going to use pure methyl dichloride. So our solvent is going to be 100% pure, which means this problem is going to be very simple, and using a simple batch process. And then the distribution coefficient for the steroid is 110. So far we never used this term distribution coefficient, so that's why we are solving this problem. So you will know what is distribution coefficient very soon. You know that I explained how the extraction works, but so far we didn't introduce this terminology, so we will learn that now through this problem. And then what I gave you is like a few more details about the experiment. The volume ratio of water to methyl dichloride. So something like your feed solution, or volume of your carrier liquid, which is in the feed, to our solvent volume is 82. And then what I asked you is to calculate the yield. I think we already did something. Instead of yield, I asked you to calculate extraction efficiency. Both refers to the same. So we will calculate the yield, and then I also want to know the concentration of the steroid in the extract. I also want you to calculate what's the concentration of your solute in the extract side, and then assume dichloride, or let's assume assume solvent and carrier liquid are completely immiscible. So that makes our life a bit more easier. So you all know how the extraction works. You have feed, you have your solvent, you have your raffinate, we have extract, and then we something like X is something like the XF is the solute fraction in the feed, and then X1 is the fraction of solute in the raffinate side, and then Y1 is the fraction of solute in the extract side, and Ys is the fraction of solute in the solvent side. So, and so far if we look throughout our lectures, we used the units. We expressed F, S, R, X, everything in terms of mass, something like kilogram of feed. Even in the previous problem where we removed acetone from its aqueous solution, we express everything in terms of kilograms, all in terms of mass units. And then the fraction of solute, we expressed everything in terms of fraction, like weight fraction or mass fraction. But now we are going to use slightly different units. So what we are going to use is like we are going to express in terms of F in terms of volume unit. So say some liters, S in terms of some liters of solvent goes inside, then some liters of raffinate comes outside, some liters of extract comes outside. Yeah. So before, in all the problems, we already converted volume to mass based on the density. So we know density is equal to mass by volume. So mass is going to be density multiplied by volume, and then we know how much mass of E, how much mass of R, how much mass of F, how much mass of S. So that's what we did so far. But here we are just using everything in terms of volume based unit. So F, S, R and E all are expressed in terms of volume, and instead of weight fraction we are going to say directly in terms of grams per liter. So that's even simpler. Yeah? Say like imagine if your feed solution contains say just for example 3 components. This has nothing to do with problem. So this is we have say 1 liter of our feed, and then we have 3 components A, B and C, and then say the concentration of A is say like a 0.1 milligrams per liter, C is 0.1 milligrams per liter, and then B is 0.1 milligrams per liter. So if I ask you so what is this? Instead of weight fraction or mass fraction, we are just expressing in terms of concentration. So concentration. So if I can show you, if you want really simple, say like 1 liter something goes inside, and 0.1 milligram per liter of A, 0.2 milligrams per liter of B, and then you say like 0.5 liters and 0.5 liters, and then if we get 0.1 milligram per liter in the top, so the remaining, what will be the concentration here of A? So this is just a component A. So what will be the concentration of A in the stream 2? You have to apply the same formula, like say like mass in that goes equal to mass out, and then F into concentration of A, that will be equal to, so let's call this stream 1, stream 2, say like let's call R and E. So R multiplied by concentration of A plus E multiplied by concentration of A. So the mass balance rule is the same. So 1 multiplied by 0.1, that's equal to 0.5 multiplied by 0.1 plus 0.5 multiplied by Ca. So from this we can calculate concentration of Ca in the stream E. So it's the same rule. Instead of mass fraction, we are expressing in terms of concentration, milligrams per liter, and then the mass, instead of mass, we are expressing in terms of volume. So if we come back to this problem, what we have here, so let me write it again. So what we have here is like, we have a feed solution, and then the concentrate that has some steroid, and the concentration of steroid XF is equal to 6.8 milligrams per liter, and then we are adding some solvent, and then the concentration of your solute or your steroid in the solvent is 0, because your solvent is completely pure, and then obviously we are going to get raffinate and extract, and then the concentration of your steroid in the extract side, how much is that? Okay, we don't have it, we have to calculate, and then concentration of your steroid in the extract side, Y1. So if you go back to your question, what I asked, assume that you have to calculate the yield and then the concentration of steroid in the extract. So you have to calculate Y1. What is Y1? Once you calculate this one, we can calculate yield. Yield is nothing but like how much, what's the amount of solute or steroid you extracted, you have in the extract phase, divide, and then what's the amount of extract you have in the feed solution. You take the ratio, so that should give your efficiency of your process. So if you get 6.8 milligrams per liter in the extract side, it means 100% yield. Yeah, so what you are going to do is like we need to calculate Y1, and then we don't have X1, we don't know what is X1, so that's what we are going to calculate. But we don't have X1, but we have distribution coefficient. So this is something I haven't introduced throughout the mod. I mean, I never talked about this terminology throughout this topic when we are discussing this topic of liquid extraction. So that's what I want to say. So what is this distribution coefficient is about? So we know how to perform a liquid extraction, we know at the end we reach to an equilibrium, and then we will have extract, and then we will have raffinate. So at the end of your experiment, the concentration of your solute, so let's say concentration of your, so let's call this as extract, and the bottom one as raffinate. So if Y1 is the concentration of solute in extract, and X1 is the concentration of solute in the raffinate. So the ratio of these two is nothing but your distribution coefficient, or the common notation is k. K is something like y1 by x1. So this is the notation we use. So that's how we define a distribution coefficient. So it practically measures the how your solute concentration is distributed on both on on two side of these phases. So if you know the concentration of your solute in the extract side, and if you know the concentration of your solute in the raffinate side, you just take the ratio that should give the distribution coefficient. I hope you all understand. And then we have this number. So what we have is like y1 by x1, that's equal to, what's that number, 170. So before we are used to use the ternary diagram. From the ternary diagram we know how to take one point, and then from there we can calculate the fraction of solute on the raffinate side, fraction of solute on the extract side based on the tie lines. But here we made the problem much more simpler using one terminology called as distribution coefficient. So what if we know the solute concentration in the extract side, then we can calculate the solute concentration on the raffinate side using this simple relationship. Yeah, I hope you all follow up to this point. And then then we have a few more assumptions. What is that? What's the assumption? Solvent and carrier liquid are completely immiscible. So what does that mean? So you start with a feed solution here, and then you end up with a raffinate and extract. You start with feed and solvent, obviously. So what does that mean? If your carrier liquid will be part of your feed solution, and then your solvent will be on the extract side, and your carrier liquid will be on the raffinate side. So after extraction, if your carrier liquid and your solvent are completely immiscible, which means all the carrier liquid which you have in the feed, that should be in R. So which means F will be equal to R. So this is some hidden information that we get based on the assumption. So F will be automatically equal to R, and why is that? And that's because your solvent and carrier liquid are completely immiscible. I hope you all can follow this one. Yeah. So in fact, if you want to prepare feed solution that we are performing in this experiment, all we need is to take 1 liter of your carrier liquid, and in that we add 6.8 milligrams per liter of steroid. So that makes our feed solution. Yeah? Just assume this one we get from some biological process, say some fermentation process, for example. So now you understand. So if you remove all the 6.8 milligrams per liter from the feed solution using a suitable solvent, whatever the carrier liquid, the volume it's going to remain same, and that will be in your raffinate side. Yeah. So that's why F is equal to R. I hope you all follow up to this point. And then first with this information, let's solve the problem. Let's perform the mass balance. Fxf plus Sys is equal to E into y1 plus R into x1. We have a feed. Feed is nothing but F, we don't have the value. Xf is 6.8 plus S we don't know. Ys we know it's multiplied by 0 because we are working with pure solvent. So the solute concentration in the solvent should be equal to 0, and E we don't know until now. And then y1 plus R into x1, and we know that F is equal to R, or r is equal to f. So we can try to simplify this expression for the moment. So 6.8 f plus 0 it's equal to ey1 plus, let's replace r with f, so f into x1. Okay, so far everything looks good. And then what else we have? Let's go back to the problem. There is something we can eliminate. We have some ratio, volume, okay, ratio of water to solvent, yes. So we have, so volume of carrier liquid to volume of solvent, that is equal to 82. So what does that mean? So we already know that both of these solutions are completely immiscible. So if you start your experiment with some amount of solvent, and that should come as your extract. If you start with 1 liter, your extract solution should contain 1 liter of yours. So which means irrespective of the concentration of your solute in the extract, so no matter whatever the percentage of x1 is here, your volume is going to remain same, and that's because your carrier liquid and solvent are completely immiscible, and so do your feed and then your raffinate. The volume will remain same. I hope you all understand up to this point. So if you have this assumption, say like so what we can do out of this, so let's give this equation some number. Let's call it as equation 2. So we can divide equation 2 by E on both sides. So we are trying to eliminate few parameters so that we can calculate the amount of steroid that we can extract from the solution, and based on the distribution coefficient. Yeah, so if you don't know distribution coefficient, then we cannot solve this problem. Or if you have a ternary diagram, then we can solve the problem. Yeah, so but for this problem is very simple. We clearly know that this solute and solvent are completely immiscible. So if you know distribution coefficient, that's more than enough to calculate how much we can extract. Okay, let's calculate it. So how 6.8 f plus equal to ey1 plus fx1. So let's divide this by, let's divide the whole expression by e. So e and e get cancelled, so we will end up with 6.f by e is equal to y1 plus fx1. So what f by e x1, and I said to you this volume of carrier liquid to solvent, that's equal to 82. So f by e, f divided by e is equal to 82. So this value is equal to 82. This value is equal to 82. Yeah, so 6.8 multiplied by 82 is equal to y1 plus 82 into x1. So we need to calculate y1. So but we have, and we don't know x1, but we have distribution coefficient. K is nothing but y1 by x1. So k value is equal to what's the k value? 6.8 170 is 170, equal to 170. So x1 should be equal to y1 by 170. So let's call this as equation 4, and let's call this as equation 3. So substitute equation 4 in 3. So what we get is 6 point, let me do the calculator. 557 point x should be equal to y1 plus 82 into y1 by 170. 82 divided by 170. That's equal to 557.6 is equal to y1 plus 0.482 y1 Hope this answer is correct. Let me check one more time. This should be equal to 1.482y 557.6. So 557.6 divided by 1.482. That's 376. I think this answer is completely wrong. It shouldn't be. I think we did some mistake. Let me fix it. 6.8. No, I think the answer is correct. 376 milligrams per liter. Yeah, I was a bit carried away by the small number in the feed solution. No, the answer is correct. Yeah, because the the volume we were dealing with a very massive volume ratio, the ratio of feed I mean your carrier liquid to solvent, that ratio is really big. So this value is correct. So your concentration is 376 milligrams per liter. I tried to solve this here one time. I solved it quickly here. So to me the answer is correct. I just checked one more time just to make sure we are not doing any mistake. So now we need to calculate yield. Yield is very simple. So we know how much mass that enters inside. So what is that? So yield is nothing but the volume of your solvent, or volume of your extract, extract multiplied by the concentration y1 divided by volume of your carrier liquid multiplied by your the concentration of solute in the feed. So this is nothing but the denominator is nothing but fxf, and the numerator is nothing but E1 Y1. So multiplied by 100, that should give percentage yield. So let's calculate that. E1 by F1, what is that? So we don't have this value of E1 and F1, but we have the ratio, carrier liquid to solvent, that's equal to 82. So here what we have is like solvent divided by carrier liquid. So F by E is equal to 82. So it should be equal to 1 by 82 multiplied by our y1 is just now we calculated 376, and then in the bottom we have 6.8. So let's calculate this one. So this value 376 divided by 82 multiplied by 6.8, that gives me a value of 0.67%. So yield is equal to 67%. So I think that's enough. So if you want, we can even call this as extraction efficiency. All mean the same. So hope this helps. So I will solve one more problem in extraction, and I think and then we can stop this particular unit operation. Yeah, so I think we already covered enough in liquid extraction. I thought to solve at least 4 to 5 more problems, I think, but this is more than enough. I think I will solve one more problem, maybe like extraction of penicillin, and then we will move on to the next topic. Probably I'm going to start with chromatography or distillation, I'm not sure. Yeah, so you will know that in the next week. I'm going to solve one more problem. This is a very simple problem. Yeah, in fact, if I give you can solve it by yourself, but still it's going to take less than a minute to solve this problem, so I thought to record it. So I'm going to read the problem. So we have some fermentation broth that contains penicillin. That's the pH of our fermentation broth, and it contains penicillin at a concentration of 180 milligrams per liter, and we need to extract this penicillin using butyl acetate as a solvent, and then we already have the equilibrium constant, which is around 57. So and the feed solution that we plan is like 420 liters, and then the extraction solvent will be 40 liters. So normally we perform this type of operation in a continuous mode, but just since we are talking about mostly about a batch liquid extraction, I just converted it into a batch process. So if it's a continuous process, this unit will be something like 420 liters per hour. So for the moment, just assume that's the volume of feed solution that we have to deal with, and then we need 40 liters of solvent to extract your penicillin from the feed solution. Yeah. So, and what I ask you to calculate is extraction factor. So this is some, don't get scared of this word. So we already calculated something, we call it as a extraction efficiency. Extraction efficiency. So we know this is nothing but equal to, what's that? This is equal to EY divided by Rx multiplied by 100. So extraction factor is just EY by Rx. So that's our extraction factor. So people use different terminologies for their convenience. If you multiply extraction factor multiplied by 100, that will give you the extraction efficiency. So it's very simple. So we can calculate. So we have, let's begin by just drawing the flow sheet. So we have feed, we have our solvent, we have raffinate, we have extract, and then the solute in extract is EX, solute in, sorry, EY, and then the solute in raffinate is X, and then solute in feed is XF, solute in solvent is YS. So what we have here in the problem, we know what is F. F is 420 liters, and then solvent is 40 liters, and then we have this ratio, Y by X ratio, that's equal to 57. So this is nothing but our distribution coefficient. So we need E and we need R to calculate extraction factor. So one thing we can do is, like, let's assume like our feed solution, instead of calling it feed solution, carrier liquid and solvent are completely immiscible. So which means the flow rate of your feed, that should be equal to flow rate, or instead of flow rate, sorry, the volume of feed, that should be equal to volume of your raffinate, and then volume of solvent, that should be equal to volume of extract. So which means F is equal to R is equal to 420 liters, and then S is equal to E, that's equal to 40 liters. So extraction factor. So this is like a 2 mark or 1 mark problem. Extraction factor is EY by Rx, that should be equal to 40 multiplied by Y, okay, 40 divided by R is 420, so multiplied by Y by X. So we know Y by X, that's equal to that's our equilibrium constant, or partition coefficient, or distribution coefficient is 57. So extraction factor is equal to 40 multiplied by 57 divided by 420. So that should be equal to, let me calculate, should be equal to 542.857. Oh, sorry, 5.42. 5.42. Yeah, I hope you all can understand this one. So if you look at this problem, we have a massive amount of feed, 420 liters, and our extracting solvent is roughly, how much is that? 420 by 14 is almost 10 times less volume that we are using to extract the penicillin from your fermentation broth. So that's why we have a very high value of extraction factor here. I think this is enough. Huh? I think in the next lecture I will make some, like how do we select a particular solvent, or what are the things that you should consider while selecting a solvent to extract something from your feed solution. And after that we'll finish the topic of liquid extraction. So thanks for listening.